Chapter 10, Section 4, Performance Metrics of Regression Models, Part 2. In the previous video, we focused on MAE, MSE, and R-MSE. In this video, I will focus on R-squared, which is often used both in diagnostic and predictive analytics. R-squared is also called the coefficient of determination. It represents the proportion of the dependent variable's variance explained by the regression equation. Since R-squared refers to the proportion of the explained variance of the dependent variable, it is denoted by percentage or proportion, for example, 56% or 0.56. Simply speaking, R-squared indicates the degree to which the predicted value of the outcome variable correctly predicts their observed value. Let's understand R-squared graphically. We have two variables, x and y. Suppose x is the predictor variable and y is the outcome variable. The green point represents an observed data point. Its x value is xi, and its y value is yi. The red point represents the point where both x and y equal their mean value. The difference between the observed y value and its mean value refers to a total variation. The worst regression model is a model that returns the average value of y for all x value, as depicted by this red horizontal line. It is useless because the regression equation returns the same y value for all x. Such a regression model does not make prediction, but just displays a representative value, the mean. In such a case, the deviance of the predicted value from the observed value equals the total variation. Suppose we have a regression model that can be depicted by this blue straight line. When x equals xi, the y's value predicted by the regression equation and the predicted data point should be on the regression line. The predicted y value is y hat. The deviance of the predicted value from the observed value can be expressed as the distance between the green point and the blue point. It is smaller than the total variation. It means that the regression model reduces the variation by the difference between the predicted y and the average y. In other words, the regression model explains this variation. So, the difference between the predicted and average value is called the explained variation. The regression model explains a certain amount of variance. So, the difference between the predicted value and the observed value is smaller than that between the average and the observed value. However, the predicted value is not the same as the observed value. There are still some deviances. In other words, the regression model does not explain all of the variations. Some unexplained variations remain. So, the difference between the observed value and the predicted value can be regarded as the unexplained variation. R-squared represents the proportion of the outcome variable's variance explained by the regression model. So, the R-squared represents the proportion of explained variation to the total variation. Based on this logic, the R-squared is computed by this formula. The higher the proportion of explained variation, the higher the R-squared is, and vice versa. Let's consider a case where the predicted y equals the observed y. In this case, the regression model makes a perfect prediction for the data point. So, the unexplained variation equals 0. So the explained variation equals the total variation. In other words, the regression model explains 100% of the Y's variation. Next, let's consider a case where all of the predicted Y values equals the average Y. In this case, the regression model always returns the average of Y, irrespective of the X's value. And the unexplained variation equals the total variation. That is, the regression model explains none of the Y's variations. As a metric, R squared has a weakness. We can increase the value of R squared by just including more independent variables. Let's look at this equation. It is a regression equation. The regression equation includes an error term written as epsilon. An error term represents the difference between the outcome's observed value and its predicted value. The R squared depends on the value of the error term, the epsilon. Suppose we include an additional independent variable, x2, into the equation. In that case, the epsilon will decrease unless the regression coefficient of x2, beta 2, is 0. It is the case where beta 2 is statistically insignificant. So, if x2 has a little impact on y but statistically significant, the residuals will be decreased, and thus the R squared will increase. In sum, even if some of the independent variables are not important, increasing the number of independent variables increases the R squared value. It is not a meaningful increase in R squared. To address this problem, we can use the adjusted R squared instead of the simple R squared. The formula is complex and mathematical details are beyond of the scope of this course. In the formula, small n represents the sample size, and k is the number of independent variables. The point here is that if we keep the sample size constant, the increase in k increases the numerator, so the second term increases. So the adjusted R squared decreases as k increases. That is, other things being equal, as the number of independent variables increases, the adjusted R squared decreases. Let's summarize the major points of this chapter. In predictive analytics, our purpose is to make prediction. We can use a various machine learning algorithm in predictive analytics. If we want to make prediction for a labeled data, we use supervised learning. If the outcome variable is continuous, we should use regression. If the outcome is a categorical variable, we should use classification. In this chapter, we have focused on regression. In predictive analytics, we should implement data preprocessing and EDA before implementing modeling. In supervised learning, we can use the holdout method for model training. Specifically, we split a dataset into a training set and a test set, and train the model using the training dataset. And we evaluate the model's prediction performance using the test set as a hypothetical new data. To evaluate the performance of a regression model, we can use various metrics like MAE, MSE, and R squared. The next chapter will provide you with explanation of these topics regarding classification. Thank you for watching. Please thumbs up and subscribe to my channel.